Hello, welcome at the lesson 6, the first session. Hello, I think we can start our session. Hi everyone. Okay, that means what we have. We will start chapter 11. Okay, and chapter 11 is a little bit different, but still calculus. Okay, that means in this week we will introduce chapter 11 by section 11.1 sequences, and tomorrow night, the Wednesday session, I will talk about the infinite series, which is section 11.2. Okay, but let's start with 11.1. If you have any question, of course you can use the chat box, okay, and ask me anytime, and I'm watching the chat box. Okay, let me move to that screen. Okay, that's what is sequence? You probably can think about like some general definition, but let's look at this. That means sequence is simply a list of numbers, yeah, which the order is quite important. That means it's the list of numbers written in the definite order. And we will have like a sub 1, a sub 2, a sub 3, a sub 4, and so on. And we can see we have a sub n. That means the index like 1, 2, 3, 4 means the order. Okay? And seeing the number n, we have to always know that n belongs to natural numbers, which is like counting numbers. 1, 2, 3, positive integer. Okay? Occasionally we will add 0, but normally the n means counting numbers, like the first term, the second term, which actually that's how we call them. Okay? The first term, the second term, the nth term. And since we're going by 1, because that's how we count, 1, 2, 3, I'm not using any fraction. That means also it's important to know how to define the next term, which is the successor of a sub n. That means if this is a sub n, the next term will be a sub n plus 1. And then we can keep adding a sub n plus 2 and so on. Do you think, can you tell me that how can I define in general the term, one term before a sub n? If this is a sub n minus 1, of course, minus 1. And I can also keep going n, a sub n minus 2 and so on. Because we can see a sub 4 and before is a sub 4 minus 1, 3. Okay, that means just the general notation. That's we know first term, second term, nth term, the n plus 1 term, and so on. Okay. And we will, in this chapter, in this section and then chapter, we will deal exclusively with the infinite sequences, which means we will have infinitely many of them, like n goes to the infinity. Okay? Yeah, lots of terms, but we will try to manage them. Okay, now what we can do. We know that n is a positive integer. We call counting numbers or natural numbers. That means what we can do, we can think that our sequence is a function, but with the certain domain. And domain is just the positive integer. That means we do have a notation different than the function for the sequence, which of course is a sub n. Okay, but we will not probably use f of n, but we can still think that this is like a function because we will have a formula. Everything will depend on n. Okay, then we have to remember just positive, like kind of like a discrete mathematics, like just the points. Okay? Something which is defined for 1, something that is defined for 2, and so on. Nothing between. Okay, that means a sub n is the proper notation for the sequence, but we may think f of n, which is corresponding formulas, but only if the domain is positive integers. And that's when this sequence is like a function. Okay, and then that's the notation. We may have the expanded form, like I can give you like the terms in the expanded form, like a sub 1, a sub 2, and so on. Or we may have just the general formula, a sub n. Okay? This notation, yeah, we will use this curly brackets. This notation is like, we can see, is indicating the first, the number of n, the value of n, for which the first term is defined. That means, of course, it's 1 and goes to the infinity. Sometimes if we like, let's say we will say, no, the first term, we have to start with substituting n equals to 3 or 4, or especially when it's something different, okay, like let's say 0. Yeah, we may add 0, but if it's 1 and infinity, we will probably see this. Then we assume the first term is 1. Okay, and then as I said, for the a sub n, the same like for the function, we will have a formula, but instead of x, we will have n. Okay, and then we have like 3 different types, or I mean, everything is the same, but it's 3 different like style of defining the sequence. We may use like preceding notation. We may use like defining formula, which is almost the same thing. It's just a little bit different in like writing down, but number 1 and number 2 is the same. Or we may like have the expanded form. We can put out the terms and always comma between them. The a sub 1, comma, the a sub 2, comma, and so on, because it's the list of terms. Okay. Okay, and then I have a few examples. Yeah, preceding notation. We may have the formula like that, n over n plus 1. Or I can rewrite as a kind of like a function, a sub n equals to n over n plus 1, or I can list all of the terms. N is 1. That I mean for the first term. For the first term, I did substitute n1, and then I substituted n2, 3, and so on. Yeah. Maybe as an exercise, do you think you can tell me how, in terms of n, how the next term will be defined? And I can write. Okay, yes, that will be 5 over 6. But I'm saying the next one after this. This one is a sub n, and then we will add 1, and we will add 1, which will be 2, and that's the a sub n plus 1. And then of course we can keep working. Okay, just to checking, because the general notation is also important. Okay, that means this is one formula, and I have just 4 different formulas, but we can see the first and the second is almost the same thing. The third kind is like expanded. It's a little bit different. Okay, we may have something like that, n plus 1 over 3 to the n, yeah? And we will use like any algebraic expression, linear function, quadratic expression, cube function, maybe trigonometric function, maybe exponential, like this one, 3 to the n. Yeah, that's when everything will be the same, but we will have just n instead of x. Okay, that's when we have n plus 1 over 3 to the n, and we do have something which probably is a new thing, because we didn't really have this for the function. Part of the formula is -1 to the n. And we can see -1, if it's taken to the power of odd number, will stay negative. What's happened if -1 is taken to the power of even number? It's positive, yeah? Because it's like to the power of 2, 4, 6, thank you, which means every other term will be negative and every other term will be positive. That's when we will call alternating sequence. When we will see this part, -1 to the n, is giving me the alternation. This is the same thing, just like function notation, and that's Yeah, that's the expanded. And we can see negative, positive, negative, positive. Yeah, it's also a certain property of the sequence. It's like alternating one. That's in please, yeah, please remember this means negative one, positive one, negative one, positive one, and so on. Okay. Okay. Number 3, I have different like example, and we can see we will start from n equals to 3. And you can guess why, because we have square root, and square root, we can't have negative in the radicand, yeah? Negative numbers. That's the same thing, and we can see this is the indication of the set of this initial point, n equals to 3, and then we just substituting 3, we have square root of 0, square root of 1, square root of 2, square root of 3, and so on. Yeah, but this is like the indication. And you may know, you know, if I'm not writing, always 1, always, we always start with 1, counting numbers. That's how we start counting. And the last one is trigonometric, which usually for the trigonometric, we will start with 0, even if 0 is not a counting number. Okay, cosine of n pi over 6, which will be cosine of 1 pi over 6, 2 pi over 6, 3 pi over 6, and so on. That's the same, yeah, just different symbols and values. Cosine of 0, it's 1, cosine of 2 pi over 6, 3 pi over 6, and so on. Okay. Okay, Abdallah is saying that you will always start with 0. Yes, because 0 is, but we, because the n is the natural numbers, and natural numbers are, that's the counting numbers. Yeah, that's kind of like more, I mean, natural is more mathematical terminology. Oh yes, if depends what we're doing, but yeah, probably when you coding, when you some software, making some, yeah, like programming, that's what programming, you may say at the beginning that we always start with 0. Yeah, yeah, but I have to say that we normally start with 1. Okay. Yeah, I even say that it's n, always n means the first number is 1, but we may start from different quantities. Okay, that's we okay with this. And now let's try, because we have to be like flexible. Okay, that means we may have an expanded form, like a sequence, a list of numbers, and we will try to find a general formula, a sub n. And we always, when we see these 3 dots, we always assume that the pattern will carry on, will continue forever. Okay, that's me having these terms, 1, negative 1, 1, negative 1. How we can find out the general formula? It's, of course, it's negative 1 to the power of 1. But we have to be, okay, we have to be careful. Yes, that's actually, that's good. But let's correct a little bit. Because when I have this way, yes, I see some correction. This means that n is 1. Negative 1 to the 1 will give me negative number as a first term. That's what I can do. I can just add 1, which means I will start with the even number. 1 plus 1 is 2, and then 2 plus 1 is 3, and will give me negative. No, we have to be, okay, you can say Abdallah this way, but don't keep negative on its own, which means the same thing. This will also work, but we will keep, yeah, because when you expand, you have, yes, we can have it, but we will prefer, I can even say 3. That's the same. This one is a little bit confusing because we will keep this negative and then the alternating part. negative times negative will give me positive. Yeah, it's still, of course, algebraically is correct, but it's better when we keep the negative together. We will have also an exercise that we have to split, but I think this is the best. Or if we will have the first term negative, positive, negative, then what will be the formula? That's probably yes, this one will be just -1 to the n. That's what I thought at the beginning. Okay, let's see the next one. Find the formula, the general formula A sub n for even numbers, 2, 4, 6, 8, 10, 12, and so on. Yeah. We always multiply everything by 2. 2n. 2 times 1, 2 times 2, 2 times 3, 2 times 4, and so on. Good. Okay, now please remember, even numbers will be 2n. Okay. What about odd numbers? 1, 3, 5. We can say 2n minus 1. This means that we're starting with 1. What about, oh, no, I want you to tell me. If I would like to start with 0, how can I define the odd number? Yes. Heather, did you say n plus 2? But when you say n plus 2, and if n is even number like 2 or 4, yes, then I will have even, and I have to have. That means but no, it's good. It's good to try and play with all of these formulas. Yes, yeah. That means now when we starting, when the first term is defined for n0, we will have 2n plus 1, because then it's 0 plus 1, and then 2 plus 1, 4 plus 1, and so on. That means 2n minus 1 or 2n plus 1. That's odd numbers. Okay, good. And then I have kind of like a random numbers, but they create a pattern. Okay, that means let's see. We have 3 over 5, 4 over 25, 5 over 125, 6, 7. That means on the top, I have 3, 4, 5, 6, 7. In the denominator is 5, 25, 125, 625. Probably that's two big numbers, but we can figure out. And also we have positive, negative, positive, negative. Okay. That means first of all, I will say -1 to the n plus 1, because the first term is positive and I want this to be even. And then we have fraction. Yes, and in the denominator we have 5 to the power of 1, then 5 to the power of 2, 5 to the power of 3, which is 5 to the n, and on the top we have 3, which means if n is 1, we have to add 2. Yes, I can see. Thank you. Okay, as we can see, we did get the formula. And I type my answer. Yeah, I put -1. Can you see it in the corner? It's still okay. We can have n plus 1 and -1. That's fine. Okay, let's look at this. This is interesting. That means what we may have. We may have like the definition that we had so far. I can even come back for a second. Let's look at this. Okay, we have the formula for the sequence in terms of n. Yeah? Another formula in terms of n. Another one, another one. Yeah? That means this is the nice, like, explicit way to define the sequence. And if I will ask you, can you tell me what is the A sub 100? Yeah, you will just substitute instead of n 100, or A sub I don't know, 51, you will put 51. That means this is the nice explicit way. We can do more things. But some of the list of the terms, some of the sequences, they don't really form the nice explicit formula. Yeah? We have the other way to define sequence, and we call like the recursive definition. Okay. That's, if everything is in terms of n, is perfect. That's the good, I mean, easier way. But we may have a sequence which is defined recursively. What this means is not defined in terms of n, is defined, one of the term is defined in terms of the other term of the same sequence, which of course we still don't know. And one of the best example of the recursive definition is the Fibonacci sequence. Did you ever hear about the Fibonacci numbers? I'm sure, yes, okay. Golden proportion, Okay, that's my Fibonacci number, Fibonacci sequence. And we can see, just instead, because it's based on the name of the Italian mathematician, Fibonacci, that's the reason that instead of A, we're using F, but it's the same, yeah, it's just the same. And the main formula is here. But always with the recursive definition, we have to have some initial information. Okay? That's when we know that the first term and the second term is 1, 1, 1. And then based on this, we can create the next terms. And let's read this. F sub n, which means the nth term, is defined as a summation, addition, okay, of two terms in front of f sub n. Okay? We can see n minus 1, f sub n minus 1, and n minus 2. That means I have to take two terms, add together, and then this will be my third term. Okay, makes sense? That means let's see. The first term is 1, the second term is 1. Do you think you can tell me the third term? Will be 1 plus 1. Because I can even substitute. If n is 3, then 3 minus 1 is 2, 3 minus 2 is 1. I have to add the second and the first term, okay? And then I can keep working. If this is f sub 4, will be 3, f sub 3 and f sub 2. Okay, that means 1 plus 1 is 2. And then 1 plus 2, we adding these two, it's 3. 2 plus 3, who can type for me? I know I can see. 2 plus 3, thank you, is 5. 3 plus 5, 3 plus 5, oh, 8, and maybe a few more. 5 plus 8, 13. Good, thank you. Good addition, and 21. And the last one maybe, because we can go forever. 34, thank you. Okay, that means that's the, and I think I type a little bit. That's the Fibonacci sequence. We can see the definition is a little bit different. And for this one, I can't really ask you like, oh, what will be the 100th term? We really have to go term by term, because of the nature of the definition, it's implicit. I can use the word, but we call it recursive definition. It's not in terms of n, which I will have this advantage to put the value for n and create my term. I have to list all of that. I always, if I would like to have 101, I have to have 99th and 98th, two before. Okay, that's we have these numbers 1, 1, 2, 3, 5, 8, 13, 21, 34. Probably we look at these numbers and we think they are kind of, okay. It's the sequence, is the one section in the calculus textbook. It's just, kind of like random numbers. Yeah, that's what we will think. But we know that that's not true. Yeah, these numbers are the beautiful numbers, even if they don't look like this. I have something. Yes, first of all, these numbers create, this sequence. Yeah? If we will look around, we can find everywhere. In the nature, if like in humans, in art, in music, they creating a beautiful golden ratio. Okay. And of course, we using this Fibonacci sequence in computer programming, sorting data, some generating number. Yeah, lots of application. And I have just a few funny pictures for you to show you. Let's see the nature. Okay, I have this nice tree, the oak, the live oak. And we will probably think that this is like the pattern. The way that the tree branches grows is just randomly, but actually no, we can find the Fibonacci numbers here. Okay, and I can show you. You can maybe you can read this, divine numbers, but I can show you more simple picture. If you look at probably any tree, they will, let's look at these big numbers. They grow, the branches actually grows like that, and they follow the Fibonacci numbers. The first one at the bottom is like 1, then it will like expand and will create 2 branches, and then only one of them will expand and we will have 3, and then 2 of them we will have 5 branches, 8, 13, 21. Yeah, you can probably go outside and look. And I also put the different numbers, but this is, that's interesting because that's also the numbers the other way, but this is interesting how they grow. And I was trying to draw a little bit more primitive. 1, 2, 3 branches, 5 branches, 8, and so on. Okay, that's one thing. But also the music. Okay, you probably know piano. I mean, maybe you play, maybe you definitely saw it. That's what we have. We have this 1 like octave, and then we have 2 and 3 numbers of each set of black notes. We can see 2, 3, 2, 3, and which together is 5 of number of black notes, and then is 8 number of white notes in 1 octave, and then 13 total number of notes. Yeah, because what's happened, people will find the Fibonacci numbers everywhere. Yeah, that's what's happened. Let me come back. That's how he actually, because he was trying to write some poem. I think I typed this for you. He was just using some pattern, and then he used some sequence, follow the formula. That's how he discovered these numbers. But then the people are using these numbers and kind of like seeing them everywhere. Yeah, which is still a little bit of mystery these days. Okay, but let's see. And what example? Let's see the nature. Let's see the pineapple. Yeah, you can even check if you have at home, or you can go to the store. We have like 5 of these pieces, and then 8, 13. Yeah, but they create something. I can show you. Oh, golden ratio. That means another property of these numbers, okay, is the ratio between 2 numbers in the sequence. That means we can say 1/1, of course, is 1. Then 2/1 is 2. But 3/2 is 1.5. 5/3 is just the ratio of 2 neighbors of these 2 numbers. 1.6, 8/5, 1.6, 13/8, 1.6. And they actually, at this, you can keep taking the ratio, and they will never be different than 1.6, like 61. Okay, and this number 1.61 we call golden ratio. Yeah, that means the Fibonacci sequence, they create a golden ratio. For example, if I will ask you, you can even try, I don't know, now you can take a pencil and I will ask you to draw a rectangle. Okay, you can draw a random rectangle, and now you have to measure the length and you have to measure the width, and take the ratio, length divided by width. Yeah, you will get you will get 1.6. If you will use you will measure the length, like you can use the ruler and you can write it down. You can measure the width. I have this. You can measure A, you can measure B, and you can divide. And I'm sure everybody will have the number around 1.6. Why it's like that? We don't know. Yeah. It's just the most, how can I say, the most beautiful rectangle, the golden one. Okay, yes, that's what we tend to do. Okay, because we always want to some proportion. Yeah, like even I have some pictures, even the human body, like, yeah, we don't have like a teeny tiny, I don't know, head and such a long, like, I don't know, legs. Everything has the proportion, and even if we are different, we keep this proportion. Yeah? And of course, people find lots of in the measurement in the human body, lots of, like, I mean, Fibonacci numbers in lots of different places, and golden ratio. Okay, also what's happened with this rectangle and golden ratio, let's look at this. We may start with this, you probably saw this spiral. Yeah, we may start with like a square, like 1 by 1, and then 2 by 2, 3 by 3, 5 by 5. This means the length of the side. And then we can draw 8, because if this is 5, this was 1 and 2, that means this is 8. And then of course 13 and 8 is 21, 21 by 21, 34, and we can keep working. And the same thing, you can measure, because this is 34 and this is 8, this is 13. When we add together and divide by 34, we will have 1 point. But that's the ratio, of course, that's here. We will have a golden ratio. Okay? And actually the golden ratio is the number, the Greek letter Phi. I don't know if, because I would like to say the Greek, which is like that, or the big one is kind of like this, yeah? Is the Phi number, 1.61. That's, we can see also the Fibonacci numbers, the spiral. Yeah? And everything, when you see, yes, yeah, when you see this spiral, like, yeah, I mean, we can see everywhere. I can show you, let's see, and then we can, and we know how, like, we can kind of like connect, we can draw and like an arc and connect in each square, and we will create that spiral. And let's look at this. Again, the Phi number, the golden ratio. That means the golden ratio, it's considered like to be just beautiful. Yeah? If something is off, yeah, you will probably see, and you will tend to correct. Like, for example, you have a picture and you have to crop. Yeah, you have to crop the picture. You will always think, no, something is wrong, and you will tend to actually to get the golden ratio. Okay, everything. That means, because it's so nice, like to see this, and that's what we like. People are using this everywhere. Yeah, as I said, in art, architecture, music, everywhere will be the proportion, because it's just the most beautiful, yeah, view, pleasing our eyes. And of course, yeah, art, yeah, the ancient Greeks in architecture everywhere. And this is also nice property, but that's the same with the rectangle. If we will take the number, the Phi number, 1.61, that means this is the only positive number that when we subtract 1 from that number, we will get a reciprocal of this number. Yeah. Okay, just, yeah, funny properties. Okay, and let's just look at this spiral. Yeah, we have spirals everywhere. Yeah, if we can always fit to, we can see the nice shell, even the ear, sunflower, some hurricane, tornado, even the egg. Yeah, everything. Oh, the music note is just, yeah. Because if something is drawn differently, then it's not pretty, and we will always try to fix it, and you will always get to the golden proportion. I have more, yeah, in human face everywhere. Yeah? As I said, we don't have like big head and tiny like dots as the eyes. No, everything has the proportion. Sunflower, galaxy, even a beautiful Africa, even the finger. What else I have? And some, yeah, human. Oh yeah, like that's the proportion in the face, in the whole body, and this is just even like, yeah, everything. Oh, the length of the bones also create not the spiral, but because we can always create a spiral and the golden proportion, but that's Fibonacci numbers. Okay, do I have something more? Oh, and then it's my picture. I was drawing this Pascal triangle. Do you know Pascal triangle? And then when we like add, yes, when we add numbers, 1, 1, and then when I add 1 and 1 is 2, 1 and 2 is 3, like the red lines created like kind of like a diagonals, and you can see we create a Fibonacci numbers. Okay, that means even if it looks so random, you can see everywhere, and people, when people do something, create something, paint something, they will always try to use the gold. I mean, they don't even know that they're doing this. Yeah. Okay. Oh yes, we can. Yeah, we can use a lot. That means looking at these numbers. Okay, they are. Oh yeah, we have lots of application. But this was just a few pictures. That means we saw connected. Everybody. Okay, that means now let's focus on the recursive definition. These numbers will be not as beautiful as the Fibonacci numbers, but let's just create and let's just compute the first 4 terms of this definition. That means we have the first term, it's 3, and then this is the definition. A sub n plus 1, okay, is defined as a half of the term 1 in front, okay, which means if I will be looking for the second term, this will be the first one. If I will be looking for the 4th term, for example, this will be the 3rd one, and plus 2. That means the second term is defined 1/2, and then the first term plus 2. That means I have to just substitute. And 3 plus 2 is 5/2. And let's get the third one, 1/2, and I have to substitute the second term. We can see if this is 3, this is always 1 less, n plus 1 n. And I will substitute. Okay, 1/2, 5/2 plus 4/2. 9/2 times 1/2 will be 4. Okay. And I can leave it this one for you. Okay, let's keep, yes, keep. Okay, yeah, it is 17/8. Okay, I will not. I will trust you because I don't remember. Okay, I know Fibonacci numbers. Okay, now sequence, okay, because what we can do as the sequence, that means now we will get back to the not the recursive definition, which we may have the recursive definition, just the nice explicit, just a normal definition. That we do have a formula n/n plus 1. And as I said, the sequences are kind of like a function that we have to know how they behave, and especially how they behave at the end of the domain, which means if n is infinity. Like, are they really like getting, like what values they getting? Oh, hang on, this supposed to be commas. Do you remember? I even like accent this. Commas, not addition. No. It's commas, it's just the terms. That's mean what we have. We have a formula, we have a sequence. That means the same like the function, we will try to investigate how they behave. And what we can do, we can draw Yeah, we can plot these points and see how the dots behaves, because not always numerically we will see this. Yeah, because you can probably see what the terms are tending to approach: 1/2, 2/3, 3/4, 4/5, 5/6. What do you think? Are the terms getting bigger and bigger? Is the sequence like increasing? I think they 2/3 and then 3/4, 4/5, 5/6, 6/7. I think the terms are getting bigger. Yeah, and 7/8, 8/9, 9/10. Let's say 99/100, 999/1000. Yeah? That means they're getting bigger and bigger, but are they increasing like without any bounds? I see on the chat box, they do have some limit. They will be never greater than 1. Yes, thank you. That's what we can do. We can plot them just using the number line. Like this. This is the number line. That's A sub n. That means this is 1/2 and this is 2/3. This will be 3/4, and we can see they getting like closer to each other, okay? And A sub 4, A sub 5, and so on, but they will be never greater than 1. But what we will do, since we have like a n as an input, as an independent like variable, and A sub n as an output, we will use the XY plane. That means we will plot them like that. Probably we will not use the 1D, we will use 2D, 2 dimension. That means on the x-axis, we have n, we have input, and on the y-axis, we have output, the corresponding A sub n values. That means for 1, we have 1/2. For 2, we have 2/3, and we can see. And then for 3, we have 3/4, 4/5, 5/6, 6/7, and so on. And we can nicely see the dotted line. It's the limit. Okay, it's simply the limit. That means now, in order to check this behavior arithmetically, or maybe calculus-wise, I will ask you this: how this expression behaves as n goes to the infinity. And we know that this is 1. As n is getting bigger and bigger, the values of the sequence are approaching 1. Limit as n goes to the infinity of the sequence. Okay? That's what we can see. It's simply like a function. We will definitely adopt all of the laws in order to compute this limit, the laws of the limit of the function. Because you can imagine x over x plus 1. Of course, it will be, we remember limits at infinity. If the degree of the function is the same, we're just taking the ratio of the leading coefficient. 1/1, it's 1. Yeah, just the technical. Yeah, but that's what we will do. And this is the main exercise for this section. Of course, we have to know all of the new thing, the terminology, the meanings, but we will compute a limit of the sequence. Okay, let's see. And now, when computing the limit of the sequence, we may get at the exact value, yeah, L. And this, of course, means that the terms of the sequence are approaching L as n is getting bigger and bigger, infinity. Okay? And now, if we have this value L, then we can say that this limit exists, right? And now the new terminology. I mean, we did have this terminology for the improper integrals. Yeah, we remember, if the integral exists, we call convergent. If the integral didn't exist because the limit was involved, we did call divergent. The same thing. If this limit exists, we will say that the sequence is convergent to that number. Because we know it's like the value 1. None of the terms is 1, but they approaching 1. But that's the concept of the limit. Yeah, that means it's convergent. If this limit is like infinity, or if this limit is completely like we can't, the limit doesn't exist, yeah, any other situation than the finite number, we will call that the sequence is divergent. Normally we can think divergent as a huge, because this will be helpful as a like infinity. Like the terms are, for example, how the even numbers, that's my sequence, right? That's our sequence from the previous slide, sequence of even numbers. How this even numbers behaves as n goes to the infinity. 2, 4, 6, 8, 10, 12. How this function behaves, how this sequence behaves. Can you tell me what is this limit? Oh, 2 times 1, 2 times 2, 2 times 3. I can draw. Of course, it's huge numbers. Thank you. 1, 2, 3. We don't even have to. Yes, plot. It's like 2x. I can draw a function. Okay, 2x. Yeah, I'm choosing the yellow for the purpose because this is like the pattern. But as I said, we don't have the numbers between. For 1, the value is 2 because we only have. For 2, the value is 4. And for 3, the value is 6, and so on. That means my sequence is just the dots. Okay, but we can see it follows like the function, like function 2x, 2n. That means, of course, this linear behavior goes to the infinity, which we will say that this sequence is divergent. It's like expanding without the bounds. Okay. Let's see what else we have. That means we have to know how to compute the limit. Okay, and if the limit exists, convergent, the sequence is convergent. If the limit doesn't exist, it's divergent. But computing the limits, it's just simply the same exercise like computing the limits of the function. Just to give you a hint. Okay. And we have just here the red dots. This is just an example of two like different sequences. The first one and the second one. I don't have really the formula for them, but the red dots represents the sequence. And we can see we may have a little bit weird like behavior, but at the end, definitely the dots are approaching the blue line. The same this one is interesting because this one, it's kind of like I always call like snake because it's like it's oscillating between the blue line, but it's definitely getting like it's approaching that line, even if it's like kind of like jumping up and down, below and above, but it's definitely approaching L. That means in both cases the limit is L. Yeah, just different. But again, the yellow, my yellow curve, it's not my sequence. The sequence is just the dots. Okay. Yeah. Oh, I was even drawing. That means this is just the theorem. If the limit of the function f of x as x goes to the infinity equals to L, and then if the function has exactly the same formula like the sequence, yeah, f of n equals to a sub n, yeah, when n is of course the positive integer, then the limit of the sequence is the same. And what this means that we just computed n over n plus 1, and we know that is 1. And what we can do, we can write a corresponding, if it's easier, the corresponding function. Okay, that means we can see it's just the same formulas, but this is in terms of x, this is in terms of n. This is function and this is sequence. So we kind of like rewriting. Okay, and that's what I was saying. The pink line, which actually should be yellow, will be a function, and the dots are the sequence. But they follow the same pattern. Yeah, and we may use the same tools. Okay. Because we can call a sequence as a function. Okay. And this is just, yeah, just the definition of if the limit is infinity, we will say that the sequence is divergent. And this is just the meaning of the limit, but we remember this from Calculus 1. Okay, let's maybe compute. As I said, we will use all of the limits laws from chapter 1. Limit of the addition is simply addition of two limits, the same for the difference, constant, outside, product, quotient, power. Limit of the constant is constant. We will adopt exactly the same properties. What is interesting, we may even adopt the L'Hopital rule. Okay, but I can show you. We may use the squeeze theorem, which means we can find two additional sequences, and if our original question is like squeeze between these two, and these two has the same limit, the middle one is forced to have the same. Add one extra and new property is this one. When we have to compute a limit of the sequence, and especially with the alternating terms, when you will see the part like -1 to the n, what we can do, we can try to take absolute value, because please remember, if we have -1 to the n, if I take absolute value, what's happened with this? What is -1 to the n, absolute value of it equals to? Oh no, because -1 to the n is 1 or -1, 1 or -1. Yes, it's always +1. Okay, that's we can nicely simplify the formula. Okay, that's mean taking absolute value of the sequence and computing a limit. And if we get 0, and please remember only 0, because I can show you later the common mistakes, how we kind of overuse this. Absolute value of the sequence, the limit is 0. Then the original formula, original sequence will also have a limit 0. Okay? That means that's just the property. And we can try, I can show you the common, find the limit of the sequence, -1 to the n, and let's say n squared plus 1. Okay, that means how this sequence behaves. We may, of course, list all of the terms, but let's just use our skills from the function, the limits and the function. That we can, we see -1 to the n. That means I will try to use the property above, and I will take the absolute value. Excuse me. If we take the absolute value, then this will become 1. N was positive number will become positive, and this is positive. And what is this limit? N over n squared. We remember which function grows faster, n or n squared? N squared, which means denominator is winning. If the denominators, thank you Heather, thank you Abdallah, if the denominator is winning, what's the answer for the whole fraction? 0. Okay, that means we did get 0. This is the conclusion, that the sequence, the original sequence, okay, it's converges to 0. It's just the limit is 0 of the original one. Okay, that's how we can use. Let's take a second example. Yes, it's because it's exactly, it's us. Oh no, not x. Probably I will write the x for the n goes to the infinity, -1 to the n, and let's say n squared over 3n squared plus 1. That means how this sequence behaves at infinity. We see -1 to the n. Okay, that means we will also try to use this property, and I will apply absolute value, and then absolute value, -1 to the n will be 1, n squared will stay n squared, 3n squared plus 1. Okay, limit at infinity, n squared versus 3n squared. Which function grows faster? They are the same. The same, yes, thank you. That means if they are the same, we need the ratio of the leading coefficients. That means the answer, thank you, Dave, the answer is 1/3. That we can see the answer is different than 0. Okay? Which means the original sequence doesn't have a limit. Okay, that means a sub n, -1 to the n, n squared, 3n squared plus 1 is divergent. Okay, yes, really good comment. Thank you. Because 1/3, I did remove the -1 to the n, which means I did remove like the positive, negative, and 1/3. This is telling me that all of the terms, they will tend to be 1/3. But with the alternating part, I will have positive 1/3, negative 1/3, positive 1/3, negative. That means not one finite number. The sequence is divergent. Okay, please remember, because as soon as you see the finite number, you will circle the answer, oh, it's convergent to 1/3. No, because it was, the original thing was the alternating. Okay, 0 is fine, because 0 means we still have positive, negative, but it's this kind of like a snake. It's getting closer and closer to 0. Okay, that's how we will use this theorem. And let's see, do I have something? Oh yeah, we know this limit. I don't even have to, this is 1, beautiful. Now let's look at this. We will read this in a minute. Okay, limit, probably you know the answer. Limit, how the sequence behaves, natural log of n over n at infinity. Yeah, we definitely have infinity over infinity. Okay? And we may think we can use the L'Hopital rule, because it's, of course, ready. Or we can think, yes, we can think on about, like, we can think in terms of the growing rate, natural logarithmic function versus the linear function. Which function grows faster? This is natural log. Actually, let me use the yellow. That's natural log, and that's the x, that's ln of x. Yeah? Of course, x, the linear function, grows much faster. If the denominator is winning, the answer is 0. Okay? We may use the L'Hopital rule, but you can see now, my notes. As I said, we will adopt all of the tools, but we have to be careful, because the L'Hopital rule is asking us to take the derivative. Okay, and when I see x and when I see this yellow curve, it's fine. They are nice continuous curve. I can differentiate. But when I will think in terms of n, I only have 1, 2, 3. I only have the dots. And of course, ln of 1, ln of 2, ln of 3, ln of 4. Because if I will think, it's just the same, the corresponding formulas. But we have to make sure that we understand the dots represents the sequence. If we have dots, we have discontinuity. When we have discontinuity, we shouldn't really differentiate. Okay? But since they follow the same pattern, like the yellow, the corresponding yellow formulas, we can definitely use it. But what some of the mathematicians, they will have a little bit of problem if you will use the L'Hopital rule using the n notation. I know that is probably a little bit crazy, but if you decided to use the L'Hopital rule, you should rewrite in terms of x. We can see it's the same thing. We can use the L'Hopital rule now, because if it's x, we're really thinking about the continuous curve. Derivative of this, the answer is 0. Yeah, that means it's just, of course, you can use the growing rates, but just in case, if you like to apply the L'Hopital rule, we have to use. We don't have like we have some, I mean, on the discussion board, you typing some answers, because I don't really see much your work, but yeah, just to be like fair to the all of the mathematicians, all of the people doing the math, we should rewrite in terms of x. But we understand, yes, we understand the problem. Yeah. I don't even know if our textbook, I think our textbook is asking, some of the textbook, they will say n is fine. We know what we're doing, okay? But we know, like when we have dots, we can't really differentiate, which we still have the discrete calculus, but that's another story. Okay, let's see, because I still didn't finish. I may ask you this way: determine whether the sequence is convergent or divergent. It's just different question asking for the limit. And what do you think? Oh, I can write how this sequence behaves at infinity. Yes, thank you, Heather. Of course it's divergent, because it's -1, +1, -1, +1. It's like oscillating. That means I can't really write the answer like that. I can simply say the limit doesn't exist. The sequence is divergent. Yeah, the sequence is divergent because the limit doesn't exist. Good. Okay. Evaluate the limit if it exists. -1 to the n over n. What do you think? It's divergent. I see the alternating part. That means I will try to take the absolute value. Yeah, that's the tool that I can use the advantage of. And now I have, this will become 1, n will stay n, 1 over infinity is 0. If it's 0, the sequence -1, oh, actually, it's the question asked for the limit. The limit of -1 to the n at infinity is also 0, because this one was 0. And we can, do I have a pic? No, I don't have a, but we can try to see, oh, that's n. Okay, maybe you can tell me just a few terms. What will be the first term? And I will put the dot. 5, 6, 7. The first term is -1. What about the second term? The second term is +1/2. And the third term, it's -1/3. And the fourth one, yes, that's what we can see, positive, negative, positive. Let me draw my snake. It's like positive, negative, positive, negative, positive. But we can see the magnitude is getting smaller and smaller, 0. That's the reason that is the original sequence has also the limit 0. Okay? If this 0 will be just the finite, positive finite number, different than 0, then we will have like oscillation. But this one definitely, it's convergent to 0. Okay. Let's maybe do, I do have more stuff, but let me check this one. Okay, let's solve maybe 1 or 2 problems, and then I will finish tomorrow, okay? Because tomorrow we have also nice section. If I not finish, as always, I will add a short video, okay? But let's see this one. Determine whether the sequence is converges or diverges. If it is convergent, if it converges, find the limit. Okay, that's what we think. This one, in order to compute this limit, we can use probably the squeeze theorem. What do you think? I can start with sine of n. Sine of any angle is between -1 and 1. right? But we do have squared, which means squared quantities are always greater than 0, and still the finite, I mean the maximum value 1, when I squared, it's still 1, okay? And now my formula, it's actually divided by 3 to the power of n. I will divide 1 and I will divide 0. Okay, and then 3 to the power of n, it's the exponential function. That means this is huge, right? As n goes to the infinity, 3 to the n is infinity. That means this is 1 over infinity, this goes to 0, and of course this one goes to 0 because it's just 0. If the two-sided limits are the same, 0, the middle one is also 0. That means this limit is 0. Converges to 0. I will maybe write. I mean, we can say the limit is 0, or, oh no, we can say the limit is 0 and the sequence converges to 0. And that's the way to say. All of the terms will become eventually tiny, small 0. Yeah, but we can see I did use the squeeze theorem. Okay, let's do another one. Yeah, this is just also the theorem from chapter 1. Like when we have to compute a limit, okay, of the formula, the function, or the sequence, like what we're doing now, of the compound function. Okay? And especially when the outer function is continuous function, then we can focus on the inside. We can compute the limit of the inside and then apply the outer. Okay? And let's see, for example, this one. What is the limit, or how the sequence behaves, sine of pi over n? Okay, that we can see sine of pi over n. Sine function is the continuous function. That means I can keep outside and I can focus on the limit of the inner. Okay, and how quantity pi over n behaves at infinity? Pi over n is infinity, pi or any constant number over big number is a small number. That means this is 0. And sine at 0, of course, is 0. That means this limit is 0. Or the sequence converges to 0. What about this one? This one is actually important. I mean, unique. Okay, unique. Because we like this expression, cosine of n pi. Of course, if I will think the same way, n pi, yeah, we will have a huge number. And how cosine behaves at infinity? Do we know how cosine behaves at infinity? It's, yeah, -1, +1, -1, +1. That means this limit is, it's definitely this sequence is divergent, or we can say the limit doesn't exist. But what is interesting, that's important, cosine of n pi. Let's see how this behaves. If this will be cosine of 1 pi, this will be cosine of 2 pi. Can you tell me, get ready for the values. Cosine of 3 pi, and maybe one more. Cosine at 4 pi. What's the cosine at pi? Can you tell me cosine at pi? -1, -1. Cosine of 2 pi. +1. Cosine of 3 pi. -1, and so on. That means I can tell you that cosine of n pi behaves exactly the same like this. Extremely important information, because sometimes instead of writing -1 to the n, we really like to put cosine n pi. But this will be the only reason that we like to have the alternating sequence, or later the alternating series. Okay, that means that's the same behavior. And of course, the limit doesn't exist. Okay, let's see what examples I have. But as I said, I will probably run a short few short videos with the examples because we know almost everything. E to the power of 1 over n. Do you think you can tell me the limit? Everybody can try. 1, because it's e exponential function, and I can only compute this limit. 1 over big number is small, e to the power of. That means this sequence, okay, converges to 1. Yeah, really nice. Okay. Okay, this will be the last question because I can keep working. This is the last one. Okay, if you can tell me this answer, you good. You know how to compute the limits. You know how the sequence behaves. Is this sequence convergent or divergent? If it is convergent or if it converges, find the limit. Okay, Abdallah is saying it's divergent, and I think it's not a right answer. I think it's a convergent, or maybe, I don't know. Okay, everybody can try. Yes, step by step. We don't have to be really fast. We have to move forward, even small steps. Okay, you can work, and we can rewrite like that. Okay, we can rewrite as an nth root, we can take the quantity to the power of 1 over n. And we have one exponent and another exponent, like if we have a quantity a to the power of x and to the power of y, we can multiply this. Yeah, that's we can multiply the exponents. Okay, everybody can give me the answer. I will check everyone. Okay, that means we will have 1, 3 to the n times this. Limit at infinity. And then we can distribute. This will be 1 over n and 3. Actually, now we have 4. We have the exponential function 4, of course, continuous function. And then I can just focus I can compute the limit of the exponent because that's where n is defined. Okay, what is the limit of 1 over n plus 3? 1 over n, of course, is 0. 0 plus 3 is 3. Okay. If you know the answer is good, but 4 cube will be the sufficient answer. 4 times 4 times 4, it is 64. That means this sequence converges to 64. All of the terms will tend to be close like 64. Okay. Okay. I don't know. Let me draw because tomorrow, please attend tomorrow's session because I will introduce the infinite series. And then we have to really understand the sequences in order to be not confused with the infinite series. Okay, that's let's see if we have 1, 2, we have lots of the first terms, but what this 64 means? Because that's important. Can you, before we finish this, because you can compute everything, but the meaning, what the 64 means, can you tell me? Heather is saying that is more, no, it's not complicated. I mean, maybe it looks complicated, but it's simply the limits. Okay, 64 means, yes, kind of like that. Like we will have some terms, probably they will be increasing, right? Because when it's 0, hang on, 1, 2, is 64 the highest number? Okay, it is the highest number. I'm just trying to, okay, who can give me the first term? I'm just trying to, I don't want to write. Let's say A sub 1. Who can give me A sub 1? I will just, because I just want, before I finish, I will finish, I promise. That means A sub 1 is, okay, that means it's a huge number. A sub 1 is when we put 1, this will be 4 to the power of 4, 256. Can you compute A sub 2 for me? Okay. I will draw it differently. You may use maybe some, yeah, we may have the product form. Okay. That means the first term is actually, this will be actually 256. I just want to draw a few and just show you 256. And what about the second term? The second term will be the square root. You may use maybe calculator, but I'm just trying to show you. Square root of, it is 128, Remy, I will believe you because I'm not. Okay, and maybe the third term, 128. Thank you, Remy, you the first one. Okay, Abdallah, thank you. Okay, maybe one more, A sub 3. A sub 3 is 128. Okay, that means we actually getting, that's what I thought, it's not increasing. That means the third term is 101.6. Okay, but of course, what we have, somewhere big, somewhere infinity, yes, we can see all of that's 64. The terms are getting smaller and smaller, smaller and smaller, but they will be all of them will be at infinity as n increase, will be closer and closer to 64. Makes sense? That we know what the 64 means. 64, 64, almost at the end. If I have to list the terms, I will say 256, 128, and then I will say almost 64, almost 64, almost 64. Make sense? Okay, that means I will probably, if I didn't finish something, which I didn't, I will put the short video, but what I will do, I will definitely, a few minutes tomorrow evening will be related to that 64, because I don't want to add now, because then I will spend another like half an hour, but I just want you to, we understand so far what this 64 means, that the terms of the sequence, they are almost 64, 64, 64. Okay, that means the sequence is convergent to 64. Okay, we will get back to this in section 11.2. That means please join me tomorrow evening, like I should be at 9 p.m. Okay, and please also check the short videos. Thank you. And I'm telling you, it's not yet, like Heather said, probably it's more, it's simple, but looks maybe complicated. Okay, thank you, and thank you for staying a little bit longer. Thank you. See you tomorrow. Thank you.